Okay, here is an example that is a combination of sections 4.1 and 4.2. 4.1, finding critical points, and 4.2, finding inflection points. All right. Now, I will post this document so you can see this, but here are kind of the steps that you go through. And what you do with the first derivative, what you do with the second derivative, etc. So please use this as you go through and practice these things. All right, so this is a fun function. Just going to say, this might appear on the exam. Hint, hint. All right, so first thing we always do is determine the domain. That was step 1. So the domain, remember now, is all real numbers. E to the x is all real numbers. E to the negative x, all real numbers. I can put anything I want for the exponent. So there are no restrictions on the domain and no worries there. All right, so first derivative to find the critical points. Okay. We could also determine local max and min while we're at it. So first derivative, good review here. Once again, product rule. Okay, so here we go. Derivative of the first times the second plus the first times the derivative of the second. Now, notice the second one we use chain rule. E to the x, e to some function of x. So it's that function itself times the derivative of the exponent, which is -1. If you want to go straight to this, negative e to the negative x, fine with me. All right, once again, we need to pretty that up, and we are going to do some simplifying because it's going to help us find our critical points. So 1 times e to the negative x is just e to the negative x. Okay, here, this negative, we now have minus x e to the negative x. Okay, so this is my first derivative. Okay, so when we use our with our first derivative, we need to find our critical points. We set it equal to 0. So here is some interesting solving, and we have to solve this. We can still solve it by factoring. Factoring, greatest common factor. Both terms have an e to the negative x, so factor it out, which leaves us with 1 minus x. Okay. We did do an example similar to this back in section 4.1. We talked about the fact that e to the negative x, or e to anything involving x, will never be 0. So we will not get a critical value from that, a critical point from that factor. So the only critical points we get would be from 1 minus x. So we get a critical point of x equals 1. And that is in our domain of all real numbers. Okay, so if we were stopping here, we'd say, okay, we have our critical point. But that's not fun. Let's do the whole shebang. All right, so let's see if that x equals 1, is that a local max or min? So I can use the first derivative test, or I could use the second derivative test. I haven't found the second derivative, but I will. But let's use the first derivative test to see if it's a local max or min. Okay. So I'm using the first derivative, and I'm going to choose a test value to the, I'm going to do something here. I'm going to switch this because I want to show you something at the end. Hopefully I can get it all on one screen. But if not, no big deal. I know that seems weird, but there's always a method to my madness. All right, so choose something to the left of 1. So if I choose 0, if I put 0 back into my first derivative, whether it be the factored or not, you can do that on your own. I get a positive value. Okay, so f prime of 0, what do we get? Let's just do it one time for fun. So e to the 0 is 1. Anything to the 0 power is 1. So I get 1 times 1, which is 1, which happens to be a positive number. Okay? So choose something to the right of 0, like 10 bazillion. I don't care, but I'm choosing 3 on purpose for a reason. When I substitute 3 into my first derivative, I should get a negative number because I know 1 minus 3 is negative. Okay, so what do we know? We know that our function f is increasing and then it's decreasing, so it's changing, which tells me that at 1 we have a local maximum. So if we did the graph, that would be a highest point relative to other points around it. Okay? All right, so there's the first derivative test. So let's talk about the second derivative because we're asked to find inflection points. Second derivative helps us with inflection points. Okay? Which means I need my first derivative, so I'm going to try to make it visible. Okay, so the second derivative then is the derivative of the first derivative. Okay, so the derivative of e to the negative x is negative e to the negative x. I have to use the chain rule. Okay, now here's where we have to be careful. Minus. When we find the derivative here, this is a product. Okay, and we have to subtract that product, so whatever I get, I have to make sure I subtract everything. I'll probably regret that in the bracket. Okay, so here we go. Derivative of the first term, which is x, which is 1, times the second, plus the first, which is x, times the derivative of the second. Well, the derivative of the second is negative e to the negative x, which isn't that my original function? Okay, so I should find get the same thing again as I got for the first derivative here. But if you didn't recognize that, that's okay. Okay, so let's be careful here. So inside I have e to the negative x minus x e to the negative x, which hopefully you see is the first derivative. The tricky part here is you have to distribute the negative sign through. Got to be careful with those. So I end up with e to the negative x minus e to the negative x plus x e to the negative x. Okay, now these are like terms. Negative 1, which gives me negative 2. Okay, so here is my second derivative. Okay, the second derivative is what helps us find inflection points. Okay, so inflection points or potential inflection points are where the second derivative is equal to 0. Okay, so let's find those. Once again, can't get rid of that. Oh, I just can't surprise you. It's so sad. All right, so what are we going to do? We're going to, oh, whoops, I'm sorry. We're going to set that equal to 0. And factor. Notice how I have a common factor again of e to the negative x. So factor that out. E to the negative x leaves you with negative 2 plus x. You can always rewrite that as x minus 2. Totally fine. Nope. No, nothing will make that 0. So the only potential inflection point would be at x equals 2. Okay? Yeah, I gotta get this out of my way. All right. So let's determine if the concavity changes there. At 2, all right? So we do the number line deal again. And we're substituting into the second derivative. Okay, now I'm choosing certain values for a reason. 2 is my potential inflection point. So I'm going to choose 1 and I'm going to choose 3. Now let's go back up here. 1 is a critical point. So by substituting 1 into the second derivative, I'm doing the second derivative test, so that'll be kind of cool. We'll see if we get the same result. The fact that 1 is a local max. Okay? So substitute 1 into the second derivative and we get a negative value, which tells me that the graph of my function is concave down. So let's think about that. 1 is a critical point. I got negative, which tells me that I have a local max because the function's concave down. So that's the second derivative test. All right, if I plug 3 in, I get positive in the second derivative, which tells me that the function is concave up. Okay, so notice we're going from concave down to concave up, which tells me that we do have an inflection point at x equals 2. Okay, we can then put those values in to the function. So my inflection point is going to be at 2f of 2, which is 2e to the negative second. Okay, so here's my inflection point. If you're going to use Desmos, turn this into a decimal. If you want to check it, that's 0.27, by the way. Okay. If I go back up here to my critical point, or sorry, my local max, that would be the point 1 f of 1, or 1. I think it's e to the negative first. I forgot to write that down. Oh, yes, I did. Sorry, I see it. So this would come out to be approximately 0.368. Okay? So let's check our results. Putting those two together, which is really hard to show on one screen, here's the graph. Another fancy Desmos graph. I love Desmos. Okay, so what have we got here? We've got our critical point at 1, okay, which is a max. So this is that e to the negative first, and then we've got our inflection point. Inflection point, critical point. All right, and this value here is 2e to the negative 1. There you go, fun times.